Okay, let us start with a theorem. The statement of the theorem is as follows: in an inner product space S with induced norm, the inner product of x y of two vectors x y square is less than or equal to the norm of x square times the norm of y square. So, this is the statement of the theorem. So, let us try to prove this result. So, let x and y be any two vectors in this space S. Let us choose an alpha that belongs to the set of real numbers given by alpha equals the inner product of x with y divided by norm of y square. Let us choose this quantity, we will see how this is connected. Now, we know from our basics that the norm is 0 or it is positive. So, therefore, 0 is less than or equal to norm of x minus alpha times vector y square. So, let us expand this norm. So, this is basically written as the inner product of x with x minus 2 times alpha times inner product of x with y plus alpha square times the inner product of y with y, right. So, this we will plug in this quantity alpha here. This is basically the inner product of x with x minus 2 times this is inner product of x with y, substitute alpha alpha is a positive quantity. So, even if I put a mod here, I mean I can just put a square here because it is anyway a positive quantity, norm of y square times inner product of y with y. And yeah, this is an alpha square here. So, this has to be power 4. Okay. So, let us simplify this, and this is basically norm of y square. This quantity is basically norm of y square. I will just put this in red. Okay. So, this would just cancel. You have a norm of y square in the denominator, and you have inner product of x y square that appears in the numerator. So, let us just take this forward. So, therefore, we have 0 less than or equal to So, this is okay. So, what we have to do, yeah. So, what we do is we have a norm of x with x. I mean, we take the inner product of x with x. So, this can be written as norm of x square. This is 2 times the inner product of x with y square upon norm of y square plus the inner product of x with y square upon norm of y square. So, what we do, slightly down, 0 is less than or equal to norm of x square minus norm of inner product of x with y, inner product of x with y square upon norm of y square. So, I think this is what we had to establish. So, this implies that the inner product of x with y square is less than or equal to norm of x square times norm of y square, and this holds with equality if vector x is alpha times vector y. And this is a very important inequality. This is a very important inequality, and this is called Cauchy Schwartz inequality. And you will see the consequences of applying Cauchy Schwartz inequality when you have to deal with match filters and so on and so forth in signal processing. So, this is a very important tool or a very important and useful inequality. Questions or examples to ponder upon. First is as follows. Can we use the Cauchy Schwartz inequality to show that the correlation coefficient for jointly distributed random variables is basically less than or equal to 1. I would say the absolute value here, the absolute value of the correlation coefficient for jointly distributed random variables is less than or equal to 1. So, correlation coefficient can be -1 or +1 on the 2 extrema, and then it has to be between -1 and +1, right. So, now I want you to use this trick that we just derived. Basically we started off with induced norms, and just from our notion of induced norms and the notion of our metric, we just arrived at this derived this equation for this inequality for Cauchy Schwartz, and I want you to use that to show that the magnitude of the correlation coefficient is going to be between -1 and +1, right. Our absolute value of correlation coefficient is less than or equal to 1. And second, define the inner product function from the Cartesian product of two vector spaces to a complex number, I mean the value that this function takes, it can be complex numbers. So define the inner product function from the Cartesian product of the vector spaces to a complex number and derive the Cauchy Schwartz inequality for this case. So I just give you a small hint why and how you can have these inner products of complex vectors that can be potentially complex, right. For example, if I look at I times, let us take the vector in the natural basis, I is basically square root of -1, right. I in even direction, and I will take say 2i or 2 times 2 minus 3i, we can choose whatever we like, you know. This is in the E2 direction. Let us say this vector is v1 and have another vector v2 which is say 2 times I in the E2 direction, in the E1 direction, plus some quantity 4 minus 6i in the E2 direction, right. So if you take the inner product, you will end up with some complex quantities here. So potentially, so what can you, how would you fix your function, and what is this notion of inner product for vectors that can have complex entries, okay. And with this definition I would want you to derive the Cauchy Schwartz inequality. Now this notion of inner products can be sort of extended to functions, right, and I think I would like to state this result for functions. Suppose I give you functions f of t and g of t defined over the interval a to b, right. This is the notion of the inner product of these two functions, and you extend this Cauchy Schwartz inequality to functions. We have the inner product of f of t with g of t. This is basically bounded by the individual square norms or the integral norms of the functions. Okay. So this is another property. So with this we can consider this inner product as a measure of some relation between vectors x and y, right. To give you a hint, let us look at x plus y square, right, and we expand it out as the inner product of x with x, then the inner product of y with y plus 2 times the inner product of x with y. So, if you ask this question, when can vectors x and y, the inner product of this, be 0, right? This is the question. I mean, we just basically think about this as induced norm. We start off with induced norm, we expand this induced norm in this form, in this form. Now, this is the general equation. Now, if I think of the inner product of x and y to be 0, then I land up with this equation that the norm square of x plus y is basically inner product of x with x and inner product of y with y, which is basically the familiar Pythagoras theorem that we have. And the intuition that we get with Pythagoras theorem is, if you have a right angle triangle, the sum of the squares of the adjacent sides is basically the square on the hypotenuse. Now, what is this x and y? If x and y are adjacent to each other and the angle between them is 0, then this holds as basically equivalent to the Pythagoras theorem, right. So, the question now is, do we have a notion for the angle between vectors, right, and that is what we will consider next. We can stop here.